Thank you so much. Yeah. Hi, everyone. It's very good to be here, and I'm very excited to talk about this exciting topic. And like Top said, like there's been a lot of buzzword around lakehouses and different table formats. So my idea today would be like to just be able to like break it down, like what's a table format? Why do we we all throughout the year we have had Hive. Why do we need a new one, right? And then I'll deep dive into the architecture. That would be my prime goal. And I will also basically like explain what happens when you do some kind of like crude operation, like reading or like inserting data. And we will end with the resulting benefits of this design approach, right? So I think I have had a fair good introduction. Currently, I'm focusing on data architectures and focusing on Lakehouse architecture specifically. But I can come from a similar like analytical background, like DI and machine learning and data science. So yeah. I'm pretty much available in LinkedIn, Twitter. I'm a community guy, so I have opened up like this QR code for you if you guys want to like just connect with me, and we can answer any question that you might have later as well. So with that, let's get started. So what is a table format? So usually with databases, we have seen the concept of tables, right? It's not a new concept at all. Like companies in the past, like Oracle or Microsoft, they have been doing it with relational databases, right? So basically, my understanding is that it's a way to organize a datasets file to present them as a single table, right? So users don't really need to know about the physical bytes and files, and they can just have that abstraction. You can use SQL, which everyone loves. You can use SQL to query the data, right? And in the past, what we have seen is that database vendors like Oracle had their own storage engine. So they handle the data files on their disk, and then there is their own execution engine, which kind of like allows to interact with this data, right? Now, in the big data world with Hadoop and HDFS, we ended up ultimately with Hive, the Hive table format. So more people can have access to data, right? But there is also a need to define a dataset schema and how do we refer to the particular dataset as a table, right? So engines or different users can interact with it, which basically gave rise to the Hive table format, right? Hive allowed the democratization part of the data using Hive query language, which is similar to SQL, right? So with Hive, we have like a table in database one, and it is composed of like one or more directories, folders, right? So as you can see, it's a representation, not of course like a real directory, but it's a single directory with a set of files in that directory, right? So let's talk a bit about this in more detail. So in the Hive table format, tables contain, like I said, is files, but in one or more directories, right? It's always inside directories. So here we can see one, obviously, but then at scale, this would be a lot of directories. And the tracking is done at a folder level. So whatever is there, it's in the folders, right? And this has been the de facto standard since the mass adoption of Hadoop and HDFS. So Facebook brought Hive for SQL and Hadoop, and there was no requirement for MapReduce jobs. Basically, it allowed to democratize data and let people really have that ability to like query that data, right? So it definitely being the de facto has been, some of the advantages, that brings it, right? And I would like to touch upon a few advantages before we really go and like, say, okay, these are some of the problems. So basically it works with every engine, right? So there was like no other table format that allowed that up until recently that we have right now with data lake table formats. So it has more efficient access patterns as well. So, partitioning schemes and mapping that to column or bucketing or, so you don't have to do full table scans for every query that you write. So it is all good. It's also file format agnostic. So you can use any file that you want, whether it's Parquet or CSV or whatever, right? And, the most important part was that it's atomically, you can atomically update a whole partition, right? So for example, you can take a whole partition, change the data, whether you want to insert some record or delete, and write the data into the new partition, right? And when you're writing it, no one sees the changes, right? And that's the best part. And then you can atomically swap that reference in the metastore. And this is how basically the Hive metastore came into the picture and allowed us to get that atomicity and consistency and those kind of stuff. So Hive metastores became the single central answer to what's in the table, right? Every engine and every user can get the same answer irrespective of what they're using and where they're querying from. And in terms of the disadvantages that we have seen, and I think I'm going to deep down more onto that, but we see that the smaller updates were inefficient, right? So because you can only atomically update a whole partition, if you only want to change a few records or like a few rows and a lot of times, then it's very inefficient. But then you also have the way to, no way to change the data in multiple partitions safely. So basically no atomicity guarantees. If you want to insert a row in, for example, 2 different partitions, right? You cannot possibly do that with, those kind of guarantees in Hive. And same with multiple jobs, like if two different engines like Flink or some other engine like Spark is trying to modify the same data set, those might not be safe for in terms of the guarantee and the trust of the data. So in the Hive table format, the files are under the folder, right? Like I said, but engine can only read files. So engine, it takes a lot of time to read by going under each and every, directory, and finally you have to read the files. So we will deep dive more on use case, which is basically an interesting one by Netflix, which basically led to the development of Apache Iceberg, and how basically it took 10 minutes for Netflix to just plan a query that for a week of the data. So that would be like an interesting one. And with Hive, users have to know the physical layout of the table. One of the application of this is basically like partitions, right? So if you have a table partition by day, and your table has data in, for example, timestamp format, like year, month, date, and like hour, minute, second, it basically has to do a full table scan. So unless users explicitly mention the partition column in the query, because the engine doesn't really know, right, if there's a mapping that can translate that particular timestamp to the physical partitioning scheme, right? So you end up with very expensive scans. And at scale, I would imagine this would be like a huge problem. And most importantly, you need to educate people, the analysts who are going to use that query to query the data. Also, the table statistics that we gathered were kind of stale, because like you need to run this asynchronous periodic job, and the data becomes stale. And since it's an expensive job, also you have to think about how often do you run the job, right? So that's something that's very downside of the Hive. So how can we actually solve this problem, right? And these problems that I kind of discussed are pretty much common. Like you might have faced an organization, and at scale this is a huge problem, right? And Netflix were kind of the main one to like look at this problem. And so they went to the drawing board, and they were like thinking, instead of putting band-aids to each and every problem, why don't we take a step back and see the actual issue, what's happening, right? Because in the long term, it's going to be really difficult, to really address each and every single issue like in one way. So they had some goals they want to achieve, and the goals were basically like they needed table consistency or correctness, which everyone wants in the organization. You need to trust in the data so that you can make this data-driven decision, right? And all the queries, if I'm running a query, I should get the same result. And then when you are running it, you should also get the same result. So that's what the expectation is, right? And we also want the faster query planning and execution. One of the queries that that I mentioned, it took them 10 minutes to just plan for a week of data, right? And users are not going to wait for that long, and the performance is like really the key in this kind of like in analytical systems. Also, they don't want to worry about the physical layer of the data. Like I mentioned, for example, partitions. I have to query using a day. Users should not have to worry about that, right? They don't have to know the physical layout, right? So can we just have the software to take care of that? Because users don't need to really know about that kind of information, right? And there were a lot of problems with table evolution, right? And this is something we see usually, like tables grow over time. Business requirements are changing. We have new requirements, schema changes. You want to add a new column. We need to embrace that, and we should be able to tackle that. And most importantly, to accomplish all of the steps at a huge scale, we can take care of a small data set. But what if I had like a huge table with petabytes of data, right? And it only grows. So when looking at this, problems and intermediate solution, and all these cons, like they went through that, they were pretty simple. Actually, the whole problem was that Hive was tracking all the files at a folder level, like I discussed, right? So the solution to that was actually very simple. What you can do is you can track the file at the file level, like let's do it at the file level. That's the core, right? So you can really mitigate those cons with this small change, and that's what basically they did. And this is where Iceberg comes and into play and addresses this problem, right? So the new way of doing this would be like tracking directly the files and not the folder, right? So coming to what Iceberg is, and we are going to like start with like Iceberg now. So coming to what Iceberg is and isn't, it's better to have that context, because we have seen that with like Hive. Hive is quite nebulous, and it can mean different things to different people. There is a Hive engine, there is a Hive table format. So I think it's important to set the motivation straight, what Iceberg is and isn't, right? So Iceberg is a table format specification. It's a table format. It's a way to manage those table data that is landing in your data lake, right? It's a way to lay out the bytes in the form of the tables, that abstraction kind of. And it's a set of libraries and APIs for interaction with that specification. So any execution engine, they have to basically leverage that table format and manage the data and process the data and do all top of analytics on top of that. And it's not a storage engine or it's not an execution engine. It's not Spark. It cannot do things of its own. It's just a format and specification, right? So as you can see in the image here, this is this is a high level, basically a high level overview of the entire Iceberg architecture and the components, right? And we will go from top to bottom and try to understand the various components of Iceberg, and at the same time we also focus on what happens when a query reads the data. So as you can see, we have the three main the components, like the catalog layer, which I would like to call here, and then there's the metadata layer, and there is a data layer, right? So the first thing here is the Iceberg catalog, right? So Iceberg catalog is one of the most important things, and if a user is trying to, or if the engine is trying to either read or write data for a table, they first need to know where to go, right, to get the data. Where do I find that information to go? What is the current information? So catalog is that place. It's a store that basically houses the current state of the table, right? So the concept is you can store as much data in a data lake, like an Amazon S3 or like ADLS, that is scalable and cost effective. But you need some kind of locking mechanism, right, for atomicity and strong consistency that most data lake don't provide for. And I think that's the kind of downside we have seen with data lake architecture, right? And now with the Lakehouse architecture, with Iceberg and different other table formats, we are trying to solve that. So catalog basically allows you to get that atomicity guarantees and make sure that we are able to make that make those queries and transactions in an efficient way. So the catalog can be a lot of things, but there is a key requirement that it must support atomic operations, right, to update the pointer of the current metadata, right? So some of the common catalog can be it can be HDFS as well, on-prem Hadoop file system, or most commonly ones on Hive Metastore or Bessie, Glue, generate JDBC. And now we also have the new REST, REST API method of invoking a catalog. So in terms of what it contains, like I mentioned, it's basically the mapping of the name to the location of the current metadata file. So this is where is the current metadata file, and you need to know to historically be able to open that file and do the operation. So what happens is, for example, if you need to do let's say select star from the database table with some kind of limit. So what you do is you go to the catalog and basically ask for the location. Hey, where is my current metadata file? Can you give me that location, right? And once we get that location, we go on and move to the next part, which is the metadata file. So now I know that okay, this is my current metadata file. So now I have that information and I can see that okay, this is my current metadata file and this is where all my information is, right? So a metadata file, as the name suggests, it basically stores metadata about a table at a certain point of time. And you can basically see from the the screenshot here that it contains the current snapshot ID, and that's something very important to Iceberg as well. And snapshot basically is a state of a table at a given point of time. So basically, whatever operations you do, like creating a table, whether it's adding a record or deleting something, everything is captured as a snapshot in Iceberg. And that allows you to do all those kind of operations that we are going to look into later, like time travel, right? And that's really important, for organization. So for our select query, we got the current metadata file, and here we get the current snapshot ID. So we know that this is our current snapshot that's getting, that's the recent one. And using that, we can get the manifest list, right? And the manifest list is just over here in the metadata, and you can use to get the manifest list. And from the manifest list, you can open the manifest file, and manifest list basically, is a list of all the manifest files, basically. So a manifest list is kind of like a list which has all the information about different manifests. In the production environment, you will probably have a lot of manifest files, right? And Iceberg, needs to keep a track of those files. And this is how Iceberg does it, using a manifest list. So we have the information here, like the manifest file path, when it was added, partition specs, and those kind of information. So for example, it can help in something like partition pruning, right? So you don't really need to go to the actual data file. So now, we have the manifest list and the manifest file, and we will read one of the manifest file, and we don't need to read all of them, right? So the manifest file gives us the actual list of the data file, and those data files can be obviously, Parquet or anything else. So along with a lot of details, and that's something really important, specifically in cases like, query optimization and this kind of stuff, right? So we see details such as the file format, which is Parquet here in the screenshot, and we see a couple of important statistics like the lower bound and the column level metrics, the upper bound of the column, right? And what is the number of NaN value counts, these are super helpful, like in terms of pruning the files and avoiding scan of all the files, thus making sure that our queries remain faster, so whatever engine you use. So this is really crucial information. So at a leaf level, if I have to say, a manifest file basically keeps a track of all the data files. And now for our query, which is like the select one, we will basically grab a data file and return it back to the engine, right? And this may seem like a lot, but this is way, way faster at runtime. So that's basically like a high-level idea. Now we will go through like a deep dive of what happens under the cover, like when you do some kind of operation, right? Create and insert and those kind of stuff, right? So let's say we start with like creating a table, like an Iceberg table, right? So let's say it's a create table statement. We have a couple of fields, and we will see basically we'll try to diagrammatically see what happens in each of the component in Iceberg, right? So on the left, you can see there is this catalog, and there is also the actual file, like the storage that you can see in your data lake, whether it's on-prem like S3 or Hadoop file system or whatever it is, right? And then, in the right, we have basically the different components, the different layers of Iceberg. So we created a table with 4 columns here, and we have the order timestamp column, which basically we have partitioned by that particular column, right? And you can see I have used like, to partition it, we've used a transformation function here, which is like the R, and we will look more onto it, but you can see that it's partitioned by a reference or a transformation of an existing column. So unlike Hive, where you would need to create a new column, you don't need to do it here. You can just apply transformation, and Iceberg, keeps a track of those transformation, right? So we created a table, and it adds, like as you can see, it adds a metadata file, right? And the metadata file will consist of all the schema details and all the information of the column and all those stuff. So the reason we don't see anything else here, or not a data file, is that we really haven't inserted anything or injected any data here, right? So that's why we only see the metadata file, which is a specification, since it's only a create statement. Next. So once we are done with creating the table, let's see what happens when you do the insert, right? And we want to insert some data, and when we go and execute that statement, we want to see what happens underneath. So let's say we want to run this particular query, right? So what happened is whatever engine you use for like this particular insert query from whatever engine you were running in, it first went and wrote the data file in the Parquet format, right? And that's the first thing it does. And when the engine is writing the data file, which is the Parquet file, it also knows the info, like the statistics that I was talking about, the upper bounds and the lower bounds, the null value counts, etc. Right? So the engine creates a manifest file with those details, right? And that's how the manifest file is here, right? So as you can see, those information that we have in the manifest, in the file form, in the table, in the actual file storage as well, like that's the manifest file, right? And then finally, the manifest file is linked to the manifest list, which is basically tracking all the manifest files, right? And finally, we have the metadata file, right? And that's the main information for us, because like we will have an engine come to the catalog and ask for the metadata file, right? That's what we went through. So remember from the first, like the create statement, we had a different metadata file, and we had this first snapshot as 0. Now, when we did the second statement, which is the insert statement, it basically what it did is it took that previous snapshot, right? And it basically took that snapshot and replaced the current one, because that's the new operation that we made, and it replaced that the current metadata file from the catalog to the v2 version 2. So as you can see in the catalog, now the version 1 metadata file is not referenced, whereas it's just version 2, which is our recent metadata file. So this is what basically happens. To sum it up, basically the engine writes the data file has all the statistics and all the information. And then the manifest file is created, and then the manifest list tracks all this information, finally updating it to the metadata level and the catalog. One last operation which I want to talk about is the upsert statement, and and this is how you might run into a lot of scenarios where you see this upsert statement coming in, right? Now, so let's say we ingested some data. Hypothetically, let's say we ingested some data into the staging table, and we want to do an upsert, right? That is, we want to do a merge into, right? So we look into the order ID, and if there is a match, what we do is we update that order amount in the table. And if there is no match, then we're just going to say, just do an insert, right? So what we'll do is we'll go and run ahead and run this statement. And let's say for our explanation and demo purpose, there is just one row in the original table that we're going to update, and there is another that doesn't exist in the original table. So it's just going to be a normal insert. So after running this particular statement, we can see the same kind of flow again, right? We have the same kind of flow now, the same kind of hierarchical Iceberg tree, from data files back to the metadata file and the catalog, right? But interesting thing to note here is that we have 2 different partitions here. Like you can see, 2 different partitions here, and we still see the original data file that we created, which are kind of grayed out. but now we have actually written a new version of it, right? So we read the original data file and we updated the order amount, right? When I was talking about we are going to update the table with the updated order amount. So we updated the order amount of file, and it was the same order ID, and we had a new order as well. So which is in a different partition. So let's say hypothetically it's 2 hours later. So that's why we have the inserted record in a different partition and the updated record in the previous partition, right? And finally, the catalog is now updated to reflect the new version, which is the version 3, right? Now we have the third operation, which is like the bird. So just to recap, every operation that we are doing is getting recorded as a snapshot, and we, as a writer, it has to be ensured that the version is referenced to the latest one, so that any new operations or any new queries that comes in, we can look into the current one and take it from there. So that's basically like at a high level what the different CRUD operation works. But one last thing would be like to understand, okay, now I have all this data, right? And I wanted to like understand how a select query works under the hood, right? So for example, the user give me the query, right? The orders, select start from table when the order date is January 26, 2021, right? So going back to the Hive world, if we had such a statement, I would say, well, I'm not partitioned by date, I'm partitioned by hour. And the partition would probably be something like 2021/01/26 and the hour of time, whatever it is. And you would end up reading the entire table unless you specify that in the statement. As a user, as an analyst, you want to like make sure that's in the statement, which we discussed is a huge problem at scale, right? So great. Now what happens with the Iceberg, right? So we will basically go through the same flow again, how we'll start here, we go to the catalog and we go and ask the catalog, hey, give me the latest, current snapshot version, give me the latest metadata file. So based on a metadata file, it retrieves the metadata manifest list. And since the manifest list we are reading here is this one, it goes to the manifest file that's being controlled by the manifest list, right? So it understands that this particular field, for example, if we talk about this particular query, it knows that Iceberg knows that this partition by field order timestamp, but the field is an hour transform of the order timestamp, right? So then now the engine can use that information and know that if they're asking for date this, it can effectively look for only partition where date is equal to 26, and from time like hours from 0 to 23 hours. And this way, it only has to scan one partition and not the other one. So this is like a very good way to like prune files and be able to like return those results in a more effective way and in a faster way. So the key really is storing that reference of the transform in Iceberg, and Iceberg does that pretty well. So let's look at another use case, which is very common in the data warehousing world and how it's also really important in the data lakehouse platforms and later lakehouse architecture, which is time travel, right? So time travel basically means you want to like, retrieve the data, from a historical, snapshot, right? You want to go back and say, hey, I want to like, I'm doing some financial reporting and I want to get like end of the week or end of the quarter data, right? How do I get that? So does Iceberg allow that? Yes, for sure. Like Iceberg, does time travel pretty well. So let's say if we do like a statement like this, like a select star from this particular table and as of that particular, timestamp, right? So after, hypothetically for this demonstration, let's say this is basically when we did that insert, but before that merge into, right? Before that upsert, right? So Iceberg is going to go follow the same path again, right? It's going to the catalog for the current metadata pointer. And from the metadata pointer, it opens the metadata file. And now in the metadata file, the Iceberg keeps the list of all the snapshot. It basically is an array of all the snapshot, right? So if you look at it programmatically, or if I have to like, explain it programmatically, it's basically an array of all the snapshots. So it consists all of them. So if you look for the current snapshot ID, there is a field called current snapshot ID. And based on the user's request, for example, in this case, it's 26 May 2021, 9:30. And in this way, it will know that the current snapshot is, let's say, S1 for this purpose. So now it will read the manifest list, right? That corresponds to that particular snapshot, right? And finally, follow the same path. It goes to the same path of going from the manifest list, the manifest file, and finally be able to get that data file. And this flow is quite similar to the, the select star with the read query that we saw, like. But this time the user has a slightly different request, which is what basically the time travel purpose was, right? So in the data lake, we will access this grade file, right? This is the grade file that was there, right? That was from a previous like operation, and we want to get that particular file data, right? So this file is not active, which is why it's grayed out here, but it's still there, right? And snapshot, obviously, like over a period of time, you can end up with a lot of snapshot. So you don't want to like you want to have an effective snapshot maintenance policy in your organization so that they can be expired. And Iceberg provides APIs to expire the snapshot and maintain it in a timely way, right? So based on your requirement, you can decide on which to keep and which not to keep. So we went through the different CRUD operations and the path Iceberg follows to, let's say, read a file or insert and those kind of operations. Now let's see how things look at scale and in kind of like production environment, like some real use case that I was talking about. So this study is straight from Ryan Blue, who basically co-created Iceberg, Apache Iceberg during his time at Netflix. It's just a presentation from him, and it's a very interesting case study. Like their time series metric system, which is called Atlas. Basically, in a month they had like 3 million files in like close to 3,000 partition, right? And their problem was that they cannot process more than a few days of data, right? If you look at the the query that I have up for you, it's a pretty basic query, right? It's like you are trying to like get like the distinct tag based on the type from their data, from their data lake, and what you're trying to do is you are trying to have a filter based on a date field, which is like just a weeks of data, like 22nd August to 28th of August, right? Now with the Hive table format where where now Ryan and his team were using it at Netflix, this particular query, it took just 10 minutes to explain the query and not even execute it, right? So just getting the files and planning, for the optimizer to like take the query, it took the majority amount of time, right? Now with the Iceberg, this particular operation, this particular query, it just with basic partition data filtering, the execution time was just 13 minutes, right? But the planning time was just 10 seconds, So really from like 10 minutes of planning time to just 10 seconds of planning time. And that's a dramatic improvement, I would say, like in terms of like the planning, right? But if you do like a mean max filtering along with the partition filtering, which is what we saw in like the presentation with all that, column level metrics in the manifest file, right? The execution just took 42 seconds from like 13 minutes. So this time the execution in total, not even the planning, it took just 42 seconds from 13 minutes. And as compared to the Hive table format, where only like, it took 10 minutes to just plan, right? And this is, I think, a pretty impressive like, use case and like to take it forward. So another key kind of capability that Iceberg provides is like the ability to do like compaction, right? Compaction is a known problem, right? We have seen in the big data world and, problem with small files, we gather like, for example, when you're doing a lot of streaming, like it might lead to a lot of like small files. And then there's this overhead on the part of the query engines that you have to every time open and read this small file, which is pretty cost intensive, like at scale specifically, right? When you're dealing with large scale analytics. So how does Iceberg deal with that, right? So the concern here is your writers and even the readers, right? They need the fresh data, right? That's what we have established, right? So get a row, write a row, but the problem is the fixed overhead on both read and write side is super high, right? So when working with data, there's always this read side versus the write side trade-off. Like, you want low latency in write side, so you get a record and you want to write it, right, as soon as you get it. But if you do this for every single record, you'll end up with one record per file. And that's basically the extreme of the small file problem, right? But on the read side, you want high throughput, right? It doesn't matter whether you have too many records in one single file. You don't have to pay the side cost. So it's fine, like, So what compaction in Iceberg allows you to do is basically balance the read and the write side data, right? So Iceberg says there is no problem with writing more data and creating small files, right? But what Iceberg APIs will enable is to compact those small files into one large file. So in the read side, there is high throughput, right? And it's fast. And this is all asynchronous in the background, the users are not impacted about it. Like, users don't even have to know about it. Versus like in Hive, where like, compaction or like update at one time or update to one single partition and only by one particular job can be done at one single time, right? Which is like a real bummer. Right? So with Iceberg, you don't have to worry about any of that, right? All these are asynchronous operations. So users always see the fresh data, right? Users always see the fresh data no matter what. And the read throughput is really high. So the performance on the read side is also really high. And a key thing to note here is that Iceberg, like I said, is not an engine or like a storage or execution engine, but it's a set of APIs, right? So scheduling and triggering and compaction work is done by like external tools, right? For example, you can use like processing engine like Spark or Dremio to like, process the data. And you can use like, schedulers, like, different kind of schedulers to like, trigger or schedule this job, right? So this is what basically like Iceberg facilitates in a much better way or in a much efficient way as compared to like the previous table formats. So now let's talk about a couple of the, we have gone through basically at a high level how we understood the architecture of Iceberg and the different components, and how we can how different query engines can take advantage of Iceberg as the table format and use it for like effective reading of files and writing of files, right? In a Lakehouse architecture. So now let's talk about the benefits in terms of the design benefits, like what Iceberg brings to the table, right? So first, you can efficiently make small updates. So since now everything is at the file level and and not a folder level, and files can only get so big, right? 128 MB or like 256 megs. So you can make a lot of changes effectively, right? So that's really, I think one of the best advantage. And Iceberg provides snapshot isolation. So the reads, basically the reads that you're trying to do not interfere with the writes, right? So and vice versa, right? And the writes are kind of atomic, right? Here you don't see things like partial writes, right? It's an atomic operation. It also gives you the concurrent write option, like where multiple engines can write at the same table at the same time. And that's one of the biggest advantage of Iceberg that we have seen. That it allows you to concurrently write data. Use models like optimistic concurrency control. For example, you need to obviously have some checks in place. Like you will modify the files, but the file needs to be at least present, right? So using techniques like optimistic concurrency control, you can have multiple engines write at the same time, right, on the same data. This also allows faster planning and execution. And the key here is that the list of files is defined on the right side, right? OLAP analytics in general is like write once and read a number of times. So Iceberg questions about that cost, right? Like, why do we have to collect all the statistics, etc., when reading, right? And specifically when we know we are going to read like 1,000 times more than write, right? So it gives that read side benefit and advantage. Same thing for kind of like the statistics, right? All the statistics, that are stored in the manifest file, they can be used to eliminate the file for, file pruning, file skipping, right? And the engine basically is the one that writes those statistics in the manifest file, right? So if engine already knows about the statistics, why not let the engine do that part, right? And because of that, we also get like the reliable metrics, right? Instead of expensive read, we do it on write. And this is a huge benefit for any cost-based optimizer, right? Any query that you issue at scale now has the right join order and those kind of stuff. And another part that we kind of love with Iceberg is that it abstracts the physical view and exposes a logical view. For example, things that I talked about, like the hidden partitioning, right? It's one of the key features of Iceberg. So Iceberg do not need to know about the physical, the column. It doesn't need to create any column, nor as a user, you need to be able to know that particular location and the physical layout of the table, right? It kind of gets that abstraction done, right? And the relation between the partition column and the transformation column is maintained, like in Iceberg, right? So that kind of gives us the advantage, right? We don't have to know about like it, and users always see the fresh data, right? Similar thing with compaction, right? We talked about compaction a bit, like how we can have a lot of small files and users don't even need to know that you're running a compaction job to create those files. So this also means the table can evolve over time, right? We didn't touch upon much in this particular presentation, but Iceberg supports full schema evolution, full partition evolution, right? And with Hive, as far as my experience goes, it has been like file dependent, right? For example, if you make changes to a table with like CSV versus Parquet, it's all going to be handled slightly differently. So it allows, Iceberg allows for schema evolution, partition evolution, and even coexistence of two different partitioning schemes, right? So the total flexibility, which also means data engineers can now transparently experiment with the table layout, right? They have more time to do focused, infrastructure stuff or, transformation stuff, right? So definitely rich schema evolution support is one of the big aspects of it, like, how we can evolve the schema without like really rewriting the entire table in Iceberg, like, that's really important. And also all the engines, they see those changes immediately, right? Any kind of change that goes into the Iceberg table, it's an immediate change, right? What basically happens is that everything is well maintained in the catalog. So that's where the current pointer is, like the current metadata references, right? So every engine, no matter what changes it is, it will go to the catalog and ask for it, like, hey, give me the the current metadata file. And so no matter of like whatever engine you're using, it's gonna be the same, right? That's ultimately like gives us a lot of benefit in terms of like how we deal with, because like with modern Lakehouse architecture, there might be different variety of tools that you're going to use. Like you can use Spark for processing or Dremio for processing. You can use Flink for streaming, or like some other tools for machine learning, right? So you need to be able to like make sure like any kind of new like tool that you bring in, they see the same data, and you are able to make it future proof, right? So that's like the idea that I had, like in general, what Iceberg does in terms of the architecture. I basically, I think one of the main important part to like go back here is that Iceberg gives us that facility now that we kind of like are moving towards the Lakehouse architecture, and instead of running those costly warehouse level operations, now we can do it like in an open table format like Iceberg and put it on top of a data lake and have the flexibility, reduce cost, and also like it kind of like gives us that ability to like have that open data architecture, which I think is super important. Given, like I said, like it makes your architecture future proof. You bring in any new tool, it doesn't matter. You're not locked into a particular vendor, right? You're not loading it to a particular vendor's warehouse, or like you're not using their own storage or execution engine to process the data. Now the data is in all the open format, and you can use any kind of engine to access the data. So in terms of how you get started with Iceberg, I think the Iceberg, I'm pretty much involved with the Iceberg community, and the iceberg.apache.org is the official page where you can see all the latest stuff that is happening with Iceberg. And Iceberg also has a curated list of blogs, which a lot of companies like the adoption has been huge. Like from Dremio, we contribute a lot. Tabular does a lot as well, and we see companies like WeCloudData and now Snowflake migrating towards that, and kind of embracing Iceberg. And so there's a lot of community stuff is happening. We want to ensure we have like a diverse community representation in Iceberg, so we can take this motivation and take those implementation ahead based on the entire community, right? So we also have like the Dremio subsurface side, which is totally dedicated to all things open source and Arrow and Iceberg. So I personally like write a lot in terms of like how the different features in Iceberg are, like how we can like improve the performance with different kind of like layouts or those kind of stuff, right? So that's a really good place as well. And getting started is also like a good way to get started. Like we have pre-built Docker files, which allows you to like get started and experiment with it at a ground level without really invoking a lot of third-party tools. So that is pretty much it. I think I can take any question that you might have as of now. Let me quickly go to the chat.
Shankar. Hey guys, if you have any questions, feel free to ask. There was a question earlier from Brian. If you update one, is it the whole table replicated with a new snapshot ID?
Yes, so every operation, like I said, every operation that you make in Iceberg is going to be tracked as a snapshot. So if you update one particular record, the entire like the entire tree that I kind of basically illustrated is going to be updated with the new snapshot. So that snapshot is going to be there, and it's going to be really helpful for those kind of like time travel operations and going back and looking historically at the data. I got a question here that says, being open source, any cybersecurity concern? Not really, because we, obviously in general with any open source, there are concerns in terms of organizational approach and how we kind of deal with that. But obviously, like the whole idea with the open data lake architecture is that Lakehouse architecture is that the data lies in open table format, right? And that's the whole idea. So I think it kind of gives that advantage to it, right? So that's something that's important. I got one from Saurav that says, if possible, can you talk about the pros and cons of Iceberg against Delta? Yeah, so I can touch on a few, like, Delta Lake is another table format, which basically, Delta Lake has two versions. One is the Databricks, the proprietary one, and one is the open source one. And also there is another format, like I'd like to mention at the same time, Apache Hudi as well, right? So these three table formats have been, there, and I haven't personally like worked in Delta space as well. But in terms of the features, I think like right now we are at like feature-wise, we are not going to have that much distinction, because we are still going to like ensure new features come in, and it pretty much is going to be same in every kind of table format. But in general, like like things like hidden partitioning, those kind of things are really important and stands out in Iceberg, right? So that's something important. And I think the implementation details also varies a lot, in terms of how you like deploy it in whether it's different platforms and how you deal with that. Also the way of managing things can be a bit different. For example, like recently in Iceberg we introduced like Z-order partitioning, like the clustering, which is basically an optimization algorithm to optimize your data fields more effectively. Delta also does that, but probably the implementation is similar, but in different perspectives and different way. So overall, the future level, the things are going to be same, but the implementation details and there are a lot of benchmarking happening. So I can also share a couple of information in terms of how the benchmarkings are and in terms of how the future level comparisons are. We also have a really good comparison article between the different table formats. I see this question from the academy. Can you talk about Hoodie? So yeah, we have a really good article that kind of touches upon Iceberg and Delta Lake and Hoodie and compares them in different perspectives, like open source contributions, like features and those kind of stuff. So I'm pretty sure I can share those information as well. I got a follow-up from Ramesh. It says follow to Brian question, how updates are scalable, like 100 updates per hour versus 1,000 updates per hour. Yeah, I think scalability is a huge aspect. I think that the whole concept of having Iceberg in the first place in Netflix was that they want to deal with those kind of updates and those kind of leverages with terms of how you scale it. So definitely definitely they are very scalable, and Iceberg is designed from ground up for that purpose. So it serves that users pretty well. I have a question from Lisa. At what stage of a company in their data cycle would you suggest migrating from Hive to Iceberg? Would you recommend this over a NoSQL database for streaming data? Yeah, good question. So yeah, I think this would all totally depend, obviously, on the use cases and applications that you want to run on top of it, and depending on your architecture. But definitely, we have seen a lot of mid-sized companies, who are targeting and who are focusing on a lakehouse kind of architecture where they get the benefits of a warehouse directly on a data lake and at a cheaper cost, right? I think that's also a very important thing to remember, right? We have the scalability and agility of a data lake, right? Which is great. Like we don't have to worry about the cost that we put into storing data in a warehouse, right? Now it's all open, and S3 or ADLS, it's really cheap right now, right? So I think it will totally depend on your use cases and applications, and what you want to do and achieve on top of your the table format, which is basically a robust architecture. So in terms of my recommendation, whether I would recommend this over a NoSQL database for streaming data, I think this is a good opportunity. In terms of streaming data, we have seen a lot of streaming happening from Flink to Iceberg tables and running again analytics like BI and ML on top of that. So definitely it's a good use case. Yeah, definitely. I see another one from Brian. It says, can you do a cache query? Iceberg has some caching option for sure. Yeah, definitely. I can share some resources in that. I haven't really worked on that particular space pretty much more in detail, but I can share some info around that. And then, yeah, definitely we can do cache query. Yeah. So I think that is all I have until now. Shao, if you want to take anything else, or I can share the presentation as well. And like I said, some of the question, I think it would make sense to share some of the links as well. I think they kind of give a good idea in terms of the benchmarking and when people are looking at different table formats. So okay, I got another one with from Ramesh. Iceberg with Hive catalog, how well it works. Oh yeah, that's a pretty common thing. Hive Metastore or Hive catalog. It's one of the most common things that I have seen. The only thing that we don't recommend is not to use HDFS in production as a catalog, because again, with the atomicity guarantees and those kind of issues, it might be a problem. So that's the only thing. But with Hive catalog, it's pretty well. It's the most standard way, right? Yeah. Any recommendations for connecting to Tableau? Yes. So obviously, in a lakehouse architecture, you have the data that is in your data lake, and then you have the different raw files like Parquet or ORT or Avro, and the table formats come on top of that, right? The Iceberg helps to manage those files. So obviously, you can connect from there is no direct way to connect from Tableau as of now with Iceberg, but obviously there are for example Dremio, the company that I work for, Dremio's lakehouse platform, it directly allows you to connect that Tableau to the Iceberg data, right? You don't have to separately deal with extracting the data from a data lake to a warehouse and then be able to run Tableau or Power BI or any kind of BI or ML tool. So now you have the ability with tools like Dremio to directly run or like build dashboards around that, using the Iceberg data. I have another from Saurav. What is the adoption rate of Iceberg by various cloud provider and BI tool? So the adoption rate in terms of the industry, how we are evolving, is that we now see like a huge adoption rate in terms of the table format in general. Like we Dremio have been like we dedicatedly focus and contribute towards a lot to Iceberg. Tabular is doing that, and different vendors like now with Google BigQuery now supports Iceberg. Different Amazon Athena, like AWS Athena supports Iceberg, and different tools are coming with Cloudera, Snowflake now with external tables. So different vendors are coming with different support now plan. And in terms of the various cloud services and data lakes, S3, ADLS, GCS, whatever it is, you can use it. BI tools, that's something that you have to like rely on, for example, a Lakehouse platform that will allow you to connect to those particular data, table format. Iceberg S3 Hadoop connector versus native S3 file connector. Anything you can consider whiles? I'm not sure, Ramesh, exactly what that means, but if you want to reach out to me later, that's something I can answer that as well.